So let's say you wanted to infer on a population, and you wanted to do so in the form of a proportion. So you have a proportion here. And let's say it's the proportion of people that wake up earlier than 6 o'clock in the morning. So P is equal to proportion of people that wake up earlier than 6 a.m. But you don't actually know that proportion and if you wanted to know that proportion, you would have to do a census, um, asking everybody to record what time they woke up and then calculating the proportion from that number. And so what we can do, and that's very difficult and very expensive, but what we can do is have a sample. And in the sample, we only have to ask, let's say, maybe 100 people. 100 people. That seems reasonable. It's not as expensive. And in those 100 people, we measure the proportion of people that wake up earlier than 6 a.m. So we measure the proportion. And in this case, uh, measure proportion. And we do that by calculating the number of people that woke up earlier than 6 a.m. divided by the 100 people that we surveyed. And based on that number, we can generate a sample proportion. So proportion for this sample. So that's where this hat comes into play. This is known as our sample proportion. Now, how can we infer about the population proportion with the sample proportion? Well, we can do so only in certain circumstances. For one, let's say we measured a sample proportion where n is equal to 100, but we only did it in a select geographic area. Well, then we couldn't trust that proportion because it doesn't represent everybody. So the first key fact that any sample must have is that it must be random, must be truly random. And there are many ways to generate a random sample, but I won't get into that today. For now, we'll just say that if the problem states that the sample proportion was obtained in a random manner, that this condition was satisfied. The second condition is that it must be normal. So what this means is that when I say normal, I mean that the sampling distribution must be normal. So it doesn't make any sense for the population proportion to be normal, but it does make sense for the sampling distribution to be normal. So let's say you have the true proportion right here, and I'm just making up a number. Maybe the true proportion is 0.5. So 50% of the population wake up earlier than 6 a.m. Now, if you have p hat, your sample proportion, you took a sample and now you calculated this value, and maybe it's 0.6. You did it another time, and maybe it's a 0.4 this time. So p hat is equal to 0.4. Now you keep doing this and you have p hats all over here. P hat, p hat. What you can do is you can plot this on a table or a histogram. You'll have points here. I'm gonna erase this line so we can see it better and draw it smaller. And plot it on a histogram. And what we should see is that the distribution of the p hats of the sampling proportion relative to the population proportion is normal. Is normal. Now, we have a problem here though, because we don't know what the population proportion is, and we can't really calculate too many samples. Calculating these additional samples are expensive, and it really defeats the point of what we're trying to do here with just one proportion. So what we can do instead is we can say, well, since we only know p hat, we can generate a formula to sort of estimate whether the sampling proportion will be normal. The sampling distribution will be normal. And here's that formula. So if n, the number of people you surveyed, times your sample proportion is greater than or equal to 10, and if n times 1 minus p hat is greater than or equal to 10, then you can assume that your sample, the distribution of your sampling proportion is approximately normal. So you can assume that it's approximately normal. Now you don't really know for sure. And even if you do all of this stuff, you still don't know if it's going to be completely normal. But you can say that it's going to be approximately normal. Make that fair assumption. Now the last step is the independence. This independence condition that this proportion must satisfy. And that is, you have to take your survey, but you can't take it with surveying too many people. Because what happens is you're trying to do a random survey. So if you have 5 people, you're trying to do a random survey, but you can't when this guy gets the survey and you move on maybe to this guy next, you can't tell both of these people to leave and then conduct a random survey with only these 3 people, because let's say you have this guy here. He has a 1/5 chance. He's the first guy to get the survey. He has a 1/5 chance of getting the survey. So he has a 1/5 chance. Now you have 5 people in this thing, but this guy's already gotten the survey. So when the next guy gets the survey, he only has a 1/4 chance, because guess what? This guy's already gotten the survey, so he doesn't count anymore. So this guy has a 1/4 chance. Now, see, 1/5 is less than 1/4. That means that this guy had a greater chance than this guy, which means that our survey is actually not randomly conducted. So what we call this in statistics is independence, meaning that the probability of one guy getting the survey is not affected by the probability that the other guy, or if the other guy got the survey. Now, how can we stop this? Because we can't just tell people to say, okay, well, now, after you've taken the survey, pretend that you didn't take the survey, and we're going to randomly assign it to you again. And if you get it again, then you're going to take it again, right? That's not feasible. So we have something called the 10% condition. And what that is if you're surveying from less than 10% of the population, So if you're surveying from less than 10% of the population, then it's okay to do it without replacement. And what I mean by without replacement is saying after this guy gets a survey, taking it out again, that's with replacement, meaning that you're telling this guy that, hey, now we're just going to tell you not to take, or tell you that although you've taken the survey already, you're going to take it again if you're again randomly selected. So that's with replacement. But without replacement means that once this guy has taken the survey, now only the other 4 are game for taking the survey again. So that's without replacement. And if you do it for less than 10% of the population, you are fine. So, and that's because, well, if you have a large population, if you have like, I don't know, 900 people, and you're less than 10% means like maybe less than 90 people. That means that, well, if you survey for the 89th person, so the 89th person has maybe well, you've already surveyed 88 people, so you'll have, or maybe the 90, the 90th, because you can't go up to 90, so the 89th person, you've already surveyed up to 89, so 900 minus 88 people are left. Let's do that. So 90, 89, 10 minus 8 is 2, and then 89 minus 8 is, okay, 812 people. Now, 1 over 812 isn't that much different than 1 over 900. They're somewhat similar in size. So you can see how if you survey from less than 10% of the population, it doesn't really affect the random chance that the 88th guy will get the survey versus the first guy. Whereas if you survey for more than 10% of the population, you'd survey for like 50% of the population. Now you have people that have, well, 50% of 900 is 450. So yeah, 450 here, and 1 over 900. Now you see a significant difference in the probability that the 451st guy will get the survey versus the first guy. So it's important to consider that you must always survey from less than 10% of the population in order to ensure that it's truly independent and that everyone has a random chance, an equal random chance, or almost equal random chance of getting your survey.